Good morning, class, and welcome to this lesson on circular motion on a horizontal plane. Today we will be able to set up equations with our four main forces when an object is displaying circular motion on a horizontal plane. Notice we're going to use our four main forces and we are just going to set up equations. We are not going to do any math today. We will save that for class time. So let's start off. Let's start off with the same example we've been using for a while now. Guy holding a string attached to an object, swinging this around himself. Okay? And just for the moment, let's ignore gravity. Let's just ignore gravity because that does play an effect. Let's just ignore it for right now, okay? This person is swinging an object on a horizontal plane. So, if we set up our basic equation, F net equals ma, well, this is moving in a circle, so F net equals mv squared over r. Remember again that v squared over r equals a. Okay, just a side note, v squared over r equals a, so this is the same thing. This is the same thing. And our net force is going to be tension. Tension, because tension is the force causing it to accelerate in a circle. Tension is the force requiring it to accelerate in a circle. Okay, so that would be one way to set it up right there. Okay, let's do a different one. Let's do gravity. Let's do gravity. Okay. Earth, satellite going around Earth, so F net equals ma, F net equals mv squared over r. Notice the force that is pulling the satellite down is gravity, and if you remember the equation for gravity, it is, excuse me, I messed that up right there. The equation for gravity is G, m1, mass of Earth over r squared, mv squared over r. So notice that the same mass, this is m1, m1 and m1 is the same because they're both on each side of the equation. Those cancel out. So we are left with G, mass of Earth, over r squared equals v squared over r. And notice again, r, and r are both there. Those cancel out. So G me over r equals v squared. And based on this, we can probably either solve for the velocity of this thing going around the Earth or the radius it has away from the Earth. And so what that really means is, because there's mass on both sides, it actually doesn't matter what the mass is of the object going around. The only thing that matters is how fast it's going and how far it is away. These two will affect where it's supposed to go. And if you talk to anybody who works on satellites, they're worried about these things. They're worried about these things because the whole goal is to have the satellite rotate so that way it is always above the same point as it goes around the Earth. That's a little side note. That's a little side note. So as the Earth goes around, it's trying to be at the same point all the way around. But that's besides the point. So I want to point out one other thing here. The radius is a distance from the center to satellite. Center to satellite. A lot of times they'll say this satellite is, 3,000 kilometers above the Earth. Well, it's not just 3,000 kilometers. It's 3,000 kilometers plus the distance from the Earth to the center. So you might need to look that information up in your book if a question asks you something like that. Okay, so that is two forces already. Out of the four, we've already covered tension and we've already covered gravity. Let's move on to another one. Let's cover friction. This is going to be a top-down view. Top-down view. We are looking at a turntable, and there's going to be like a penny or a coin sitting on the turntable, and it's rotating around that way. Okay, rotating around that way. Well, it is rotating around and it is not sliding. It is not sliding. It is staying in the same spot. It is just going in a circle. How do we set that up? Well, F net equals ma, F net equals b squared over r, because it's moving in a circle. F net, the only thing holding this thing on, the only thing holding this on is not gravity, it is not tension, it is going to be friction. So friction is holding this on. So we can expand this friction into mu static friction, because it is not moving, it is not sliding. Static friction times the normal force is equal to m b squared over r. So once again, depending on what we have here, we can solve for r, we can solve for the coefficient, we can solve for normal force, and typically, notice, remember normal force, if we move to a side view, this is going to be a side view, this is the turntable, and this is the coin sitting on the turntable, so it's rotating around. If we draw a free body diagram, normal force is going to equal m1g, and friction is going to be holding it in. Well, if normal force equals m1g, that means the coefficient is m1g, which equals mv squared over r. Notice again, the m's cancel out, and so we are just left with this. So it doesn't matter what the thing weighs, it only matters what the coefficient of friction is, how fast it is going, and how far away it is from the center. So that's how we'd set it up for a static friction one. Okay? I'm going to bring up the same situation. It is a car turning. A car, this is going to be this is a back view. So I'm looking at a car from the back. These are the tail lights. Okay, tail lights, trunk. So we're looking at it from the back. It is turning to the right. It would be the same exact situation as the one down here. Mu static equals m1g, which equals m b squared over r. The only reason I bring this up is because this is still static friction. This is still static friction. And that's usually a confusion because the car is moving. The car has a velocity right here. The car is moving. It has a velocity. Why is it static friction? And it's static friction. It's static friction because the wheels aren't sliding. They aren't sliding. Or skidding. So these wheels aren't sliding, they aren't skidding, therefore it's still static friction. If they were sliding or skidding, we would use kinetic friction, but that's a whole other ballgame. We're not going to get into that right now. So we'll do a couple more. This is going to really be the most probably complicated one. Let's assume this is kind of a weird setup here. So we have a plane here, and we're going to call this like a puck. That is a puck. It is traveling in the circle, and this is an air table. This is an air table, meaning no friction. It is attached to something in the center, and then this thing is attached to a hanging weight. This thing is attached to a hanging weight. So notice here, things are a little bit different now. We have a situation now. This is multiple objects. And what makes this unique is that we'll call the puck object 1, the weight object 2, or we'll say M1, M2. M1 is accelerating. And in this situation, we're going to say that M2 is just hanging weight, not accelerating. So M2 is not accelerating. So this is our first multiple object problem where one is accelerating and one is not. Okay? So once this is accelerating inward, this one is hanging still. So if we did a free body diagram, we'll do M2. We'll do this one first. M2 is just going to be tension is holding it up. M2G is pulling it down. Gravity is pulling it down. And if we look at M1, then M1G is pulling it down, and normal force is holding it up, and tension is pulling it to the left. Okay? So if we did our F net equals MA, always F net equals MA, in this one, for M2, F net equals 0. F net equals 0. So therefore, T minus M2G equals 0, and therefore T equals M2G. Okay? T equals M2G. Now if we did our other one, if you don't mind, I'm going to erase some so we can still see everything here. Sorry about that. If we look at M2, I'm going to change that real quick. I want it to stand out. M2, F net equals MA, F net equals mv squared over r, and the only force causing it to accelerate is tension. Tension is causing it to accelerate because tension is the one pointing center. Normal force and gravity are going to cancel out. That doesn't matter. They're not accelerating. We're not concerned about those. Tension is causing it to accelerate, and tension here is equal to M2G. So M2G equals M1 v squared over r. M2G equals mv squared over r. So depending on our velocity, radius, and and M1, M2, and M1, we can solve for any one of these that we're looking for. Okay, we can solve any one of these that we're looking for. I am going to point out another example. It is a very similar example with hanging weight, but this time it is not this. We are twirling this object around in a circle. We are twirling this object around in a circle, but it is not. It is not supported. It is not supported. This is also hanging, so gravity is acting upon it. Tension is acting that way. Gravity is pulling it down. And so what is gravity going to be equal to? Gravity is going to be equal to, if we break this down to its components, gravity is going to be equal to the vertical component of T, and the centripetal force is going to be equal to the horizontal component of T. Centripetal force is going to be equal to the horizontal component of T. Okay, this is a pretty advanced setup here, something that we're going to work on in class, and if there's any other teachers watching this video, I suggest you do this kind of problem with your students in class, because if they can do that problem, then they can do all the rest of them.